So in this example, we have two parts. The first part is to find the partial sum S6. So to find S6, we're just going to add up the terms of this sequence from n equals 1 to n equals 6. And I have that listed here. And when we add that up, we get approximately 0.83282. The second part says, consider the partial sum, S6, as an approximation of the entire series S. Use the remainder estimate from the integral test to compute the maximum error of this approximation. So when we look at the entire series, the question is saying that we can estimate it with 0.83282. And now it seems a little bit bizarre when you first think about it that we're estimating 6 terms for a series that is unbounded. But when you take a look at this sequence is going to decrease very quickly because we have n squared plus 1 in the denominator. So once we get past 6, those values are going to be pretty small, and when we add them up, it's going to be a small difference. So that is why we were able to estimate with S6. Can we estimate with S7 or S8? Yes, we can. So that would be up to you how far you want to go out to estimate. But this question is stating to estimate it with the first 6 terms. Now we know that if we go from n equals 1 to infinity, that would be the same as going from n equals 1 to 6 plus n equals 7 to infinity. Because this is the first part of the series that we're adding up, and then this is from the rest of it that we're adding up. Because we're using n equals 1 to 6 to estimate the series, whatever is left over that we didn't add in is going to be our error. We need to find this, the sum of n equals 7 to infinity, to find our error. However, this is going to be difficult for us to find based on the knowledge that we have as of yet in this class. So we are going to, rather than try to compute this by hand, we're going to use the integral test. And of course you can use technology to find this value, but doing it by hand would be very difficult for us at this point. Now, the question is saying to use the remainder estimate for the integral test. So if I set up an integral with the function that represents this sequence, 1 over x squared plus 1, and I integrate that from 6 to infinity, this integral is going to give us a bigger value than the sum. Because from 6 to infinity, for this integral, this function is continuous, so we have all the values in between n equals 6, n equals 7, n equals 8. We're counting all the values in between. This is discrete, where it's only doing the terms with the whole numbers. This is finding the value of the function at all points between 6 and infinity. So this is certainly going to be bigger. Now, in order to use the integral test, we need to make sure it satisfies 3 conditions. The first condition is that it's decreasing. And this most certainly is decreasing because the bottom is going to get larger and larger and larger. So the entire fraction is going to get smaller and smaller. The next condition is that it's continuous. This is definitely continuous because with being a rational function, the places that we would be concerned about it being discontinuous would be where we have a hole or an asymptote. And the only way that we could get a discontinuity would be if we have 0 in the denominator. And the only way to have 0 in the denominator would be if we plug something in for x squared and we get out a -1, which is clearly not going to happen with real numbers. So that makes the second condition, it's going to be always positive. That was the third condition. This is always going to be positive because no matter what you plug in for x, the square is going to make it positive. And when you add a positive number to a plus 1, it's going to remain positive. So this meets all of those three conditions. So all we need to do is calculate this integral, and this is going to be a little bit bigger than series, the n equals 7 to infinity. So this is what we consider the maximum value because it's bigger than the sum from 7 to infinity. So this is what we're going to use for our maximum error. So all we have to do is calculate this improper integral. So when I find the antiderivative of 1 over x squared plus 1, that's inverse tangent. So we're going to find the inverse tangent from 6 to infinity. Now, because this is infinity, we need to take the limit when we're looking at that term. This should be a t, my bad. If you're taking notes, please change that to a t. Now, if I take the limit as t goes to infinity, the inverse tangent is going to approach pi over 2. For the lower limit 6, that I can just directly plug in. So when I take pi over 2, which was the limit of the inverse tangent, and I subtract inverse tangent of 6, we get an approximate value of 0.165149. So this is what we're using for this improper integral, and it's going to be greater than the series from 7 to infinity, which means this is going to be the maximum error.